Hello and welcome to this video about concave mirrors. We're going to look at what concave spherical mirrors are and how we draw ray diagrams for them, and calculating magnification for curved mirrors and calculating image location for curved mirrors. If you'll notice this picture here, you can see that an image is being produced that is larger than the object itself. The image of the hand is larger. If you look in the previous slide, it was smaller. The image was smaller and inverted, actually. So curved mirrors can be used to produce images that are larger or smaller than the object. What is a concave spherical mirror specifically? A concave spherical mirror is an inwardly curved mirrored surface that is a portion of a sphere and that converges incoming light rays. So if we were to look at a diagram of a concave mirror, it would look like this, where this part right here is the mirrored part of the mirror. Some basic vocabulary. C right here is the center of curvature, and R is the radius of curvature. That's the distance between the mirror at the very center and point C. This distance right here is actually equal to the radius of the spherical shell from which the mirror is a small part. This radius of curvature is one of the factors that determines where the image will appear in a concave spherical mirror and how large that image is in relation to the object. For concave spherical mirrors, incoming parallel light rays will reflect off the surface and they will converge at a point. And this point we call capital F the focal point. The distance between that focal point and the surface of the mirror perpendicularly and at that angle is called the focal length, and it's denoted with a lowercase f. If an image is being reflected, the focal point would be the place where that image is sharp and clear. Distances here and here would see that the image would become blurry, but the focal point would be where it is clear. An image of this kind is called a real image, which is different from the virtual images we were looking at before. Real images actually have light rays creating them. The actual light rays are hitting them, so they can be displayed on a surface like images on a movie screen. One important thing to note here is that the focal point can be found because it is always equal to 1/2 of the radius of curvature. So when we look at the radius of curvature and that distance, that length, 1/2 of that length will give us the focal length. And so we will always be able to know, as long as we know the focal point or the center of curvature, we can always calculate the other one because that focal point is 1/2 of the radius of curvature. So how can we determine what kind of an image an object will form for a concave spherical mirror? We're going to look at some rules for drawing ray diagrams, and there are some rules for drawing reference rays. When we draw reference rays for concave spherical mirrors, we draw 3 of them. And the first one will be drawn from the object to the mirror parallel to the principal axis. So here is our first ray that we're going to draw. Here's our object, and we're going to pick a spot on this object. I'm just going to pick the very tip of that flame. We draw a line with our ruler, very parallel, from that object to the mirror that runs parallel to the principal axis. Right here is the principal axis. Then that ray is reflected from the mirror through the focal point. And we know how to do that because we can draw a normal line here. We know the angle of incidence equals the angle of reflection. And so we'll be able to determine where that ray will go. And when it crosses through the principal axis, that point is going to be the focal point. The second ray that we're going to draw will be from the object. And since we know the focal point now, F, we will draw that right through F, and it will hit the mirror on the other side. And then the ray will be reflected from the mirror parallel to the principal axis. We will then draw ray number 3. Again, starting at our same point on our object. This ray will go from the object through C, which is right here. And when it hits the mirror, it will travel from the mirror back along itself because this is going to be perpendicular to the mirror surface right there. From here, we can then determine what kind of image is formed. The point at which these 3 rays intersect will be the same point as the object's point, but this will be the image. In this case, we have a real image. The actual rays are forming the image. It's not a virtual image. Now, in this case, our object is located in front of this concave mirror at a distance that is not just greater than the focal length, but even beyond the center of curvature. So when an object in front of a curved mirror is at this distance, the image that is going to be produced by the concave spherical mirror will be a real image. It will be inverted, and it will also be diminished or smaller in size. So how can we determine how diminished the image will be? Well, we're going to look at the magnification equation to determine that. But before we do, we have a few more conventions to explain. One, the distance from our object to the mirror, right along that principal axis, is going to be denoted by a lowercase p. The distance from the image to the mirror is going to be denoted by a lowercase q. Sometimes the symbol d for distance and sub o for object, it will be used for the distance from the object to the mirror, and sometimes you'll see the distance from the image to the mirror being represented by d sub I. We also need to explain the h. You might have guessed it's for height. H with a lowercase I is going to be the height of the image. H with a subscript O is the height of the object, and H prime would generally be referring to the height of the image, and just an H, height of the object. Here's our magnification equation. So magnification is going to equal the height of the image divided by the height of the object. We can also write the magnification equation in terms of P and Q. We can have the negative distance from the image to the mirror divided by the distance from the object to the mirror. Now, what does this M tell us? Well, if an image is smaller than the object, the magnitude, or its capital M, of its magnification is less than 1. If the image is larger than the object, this M is going to be greater than 1. Now, what about the negative sign or positive sign of the M, or magnification? If we have a real image that's in front of the mirror and M is negative, then the image is upside down or inverted with respect to the object. Please note that magnification is a unitless quantity since it's just a ratio. Now, when we're talking about making calculations, and especially this magnification equation, we need to look at a few different conventions, and these are really important to keep straight in your mind when you're doing the calculations because they will greatly affect what you get for numbers. When we're talking about this concave mirror, and this is the mirrored side, we would call this the front of the mirror. This is where we have light rays and where we have real images. This would be called the back of the mirror. No light rays are there, and this would be where we see virtual images. If we are discussing something on this side of the principal axis, it will have a positive value. Something on this side is going to have a negative value. Same with distances. If we're talking about a distance from the mirror that is on this side, that will be a positive distance. If we're talking about a distance going off on this side, the back of the mirror, it will have a negative value for the distance. And that's important to keep in mind when you are plugging numbers into your magnification equation. For concave spherical mirrors, a positive m value is going to mean that the image will be virtual and upright with respect to the object. A negative value for m will indicate a real image that is inverted. So we've been able to determine the magnification of our image. Can we determine the location of that image? Yes, we have this really nice little mirror equation. And the mirror equation can be written like this: 1 over p plus 1 over q equals 2 over r. Another way to write that, knowing the relationship between the radius of curvature and the focal length, can be 1 over p plus 1 over q equals 1 over f. So if you know how far your object is in front of your mirror, that would be p, then you could calculate q as long as you know either the radius of curvature or the focal length. And then you should be able to calculate q, and that would tell you where your image location would be. So let's take a look at this example. Say we have a concave spherical mirror that has a focal length of 10 centimeters. Here's our mirror. And we need to locate the image of a pencil placed upright 5.0 centimeters from the mirror and find the magnification of that pencil. Let's write down what we know. We know the focal length of 10.0 centimeters, and we didn't know the distance of the object from the mirror. It is 5.0 centimeters. We want to find out the distance of the image, so we can use our mirror equation. I'll use the one that involves the focal length since we're given that. Now we can just plug values into our equation and solve for q. As long as we use all centimeters, we can maintain centimeters throughout this equation. We don't need to convert into meters. And the first thing probably to do would be to reduce this into some number that we can subtract from this side. That gives us this, and we can multiply both sides by q or cross multiply, or however you'd like to think of it. And we get q equals negative, basically 10 centimeters. I wrote it so that we had the correct number of sig figs. This tells us that our image is going to be virtual or behind the mirror. Now let's find the magnification of that object. Our magnification equation equals negative q over p. And so we'll plug our values in. And since it's a negative 10 centimeters, we end up with a positive 2.0 for the magnification. This object will be the image will be slightly larger than the object. Now we can check our work by applying our ray diagram to the situation. We can draw 3 different rays for this object and see if indeed we get a virtual, upright, magnified image. First, we know that our object is 5 centimeters from the mirror, and we know that the focal length is 10 centimeters from the mirror. If this is the focal length, our object would have to be half of that distance to the mirror. So I'll draw my object there. My first ray is drawn from the object to the mirror parallel to the principal axis, and then from the mirror through F. I will extend that reflected ray out behind the mirror, and then I will draw my second ray, which is to be drawn from the object through F, which in order to do that, F is behind it. So I'm going to need to draw these as dashed lines, and then this will be my solid line from the object. And then the second part, the reflected part of ray 2, is going to be from the mirror parallel to the principal axis. So it will be going this way. I will need to again extend that behind the mirror, that reflected ray. For my third ray, it's drawn from the object through C, and then back along that ray. So I will draw that here, and then it will be dashed line behind the mirror. Now yours, of course, would be much better because I can't really put a ruler on my screen, or I can't record very well, so these are not done very well. but yours on paper would be done much better than this. And you can see that we're getting these rays converging at this point behind the mirror, showing that indeed it is virtual behind the mirror. The object will be upright. Here we have the point from our pencil here, the point will be here, and it will also be larger, which is what we calculated. So for concave mirrors, the type of image depends on the location of the object. Is the object greater than the focal length of the mirror? If so, how much greater? Is it beyond C, or is it in between F and C? Is it equal to the distance of the object equal to the focal length of the mirror? That will be different too. Is it less than the focal length of the mirror? These are all going to produce different types of images. So for our class assignment, we are going to draw ray diagrams for each of these cases to determine the type of image formed. Advanced ideas, what are some uses for concave mirrors? How do the specific images prove useful for the various purposes? Research the manufacture of mirrors. How are mirrors made? So I look forward to seeing you in class, and we'll get started on those ray diagrams.